I first introduced potential by talking about the difference in how to solve problems. You can solve problems with force, you can solve problems with energy. You can solve problems with the field, which is a force per unit charge. You can solve problems with potential, which is the energy per unit charge. But I don't want to imply that we don't, they're separate things, that we think of them separately. We often think of them together. When you look at an electric field, you might want to be thinking about potential. And when you look at a potential drawing, like I'm going to show you, you want to think about field. Because they are, of course, they are parts of the same thing. So we do look at them together all the time. So let's do that for two of our favorite fields. A charge, a big charge, which we now know acts like a point charge. And it's beautiful field lines I love to draw out, 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 out. And I have to draw 8. I don't know why. I think it looks better with 8. We like that field, and we also like this field, the uniform field. Uniform field, like that. And now we know where uniform field comes from. We must have a big plane of charge right here, creating a uniform field going that way. So there we have our two fields drawn with field lines. So let's think about the potential around these fields with delta V. So delta V equals minus the integral of E dot ds from A to B. That's our definition that we have derived. Minus integral. So first, we can go along a field line. Let's go along this field line. Start here. I'll erase the arrow from this one. We're going along the field line to here. We've walked along that field line. What is delta V if we walk along a field line? Well, ds went this way. E goes that way. This dot product is positive. So delta V is going to be negative. So that means we're going to lower potential when we walk along a field line. If this had been, say, 10 volts, this position in space, say, was 10 volts based on how close you are to this charge and how much charge it has. If you go this way, it's going to go down. Maybe this one is 8 volts. And if you keep going farther away, maybe it goes to 4 volts. And if they set up the problem right, at infinity, it'll be 0 volts, right? Because that's always the zero of potential at infinity. So if you go that way, the field goes down, or the potential goes down because of that negative sign. Because when you go with the field lines, the potential goes down. Which makes sense, because remember, it's potential energy. If you have a positive charge and it goes this way, its potential energy goes down. It gains kinetic energy. The whole story kind of tends to hold together. If it doesn't, we're in deep trouble. Now, what if you walk perpendicular? Right? So if you go this way, then something different happens. So if you move ds perpendicular to E, delta V equals 0. So this is sort of an interesting thing. So if I go that way, it's also 10 volts. And if I go that way again, it's also 10 volts. And if I go that way again, it's also 10 volts. And the way to move to keep it always perpendicular to the field lines is to move in a circle. And if this is a spherical symmetry, the lines are going radially straight out, and I go around a circle, then delta V is always going to be 0, because I'm always going perpendicular to the field lines. I could also do the 8-volt field line, the 8 volts if I wanted, as long as I stay perpendicular to the field lines everywhere I go. I'm going to map out a circle out here at 8 volts. You could go far, less far. You could just go in between. 9 volts is in there somewhere. 9 volts will also have this dotted line. Okay. So these dotted lines, what are they? These are the equipotentials, right? So equipotential means same potential, equal potential. It means basically the constant potential. It's the equipotential but it's not a line, it's a surface. It's the equipotential surface. The field we represent with lines. So you would have to do these in the plane of the board. You could have some coming out of the board, some coming into the board. We think of field in terms of the lines. It's really a flux if you want to think in terms of vector calc, but we think of it as lines. But this surface, these lines where it's constant, it's actually the, you can go perpendicular to this line in any direction in a plane, right? So these things I draw as circles are actually spheres. They're equipotential surfaces. They're not lines. In 2D, we draw them as lines all the time, but they're actually spheres. So I think, just make sure you see it, visualization lab. We'll do one of these. So here you can see our red charge and our green field lines emanating from the charge. And this gray sphere represents the equipotential surface. In 2D, we might draw it as a circle because we're just seeing a cross-section of it. Here, you're seeing the whole surface. And if I move it around a little bit, you can see clearly the field lines are going all around from the charge, but everywhere you go, the equipotential is a surface. Because that's due to the symmetry of the problem, that's where the potential is constant. Moving along a sphere, you're always moving perpendicular to the field lines. Nobody does any work, the potential doesn't change. So just keep in mind, equipotential surfaces are surfaces. So there you go in 3D. You can see these are spheres with like little lines shooting through them. Right? Everything's transparent so you can see everything. Okay, so that is how we visualize a potential field, a scalar potential field. Okay, let's look at another case. Let's look at the uniform field. It's always pointing this way. Here, maybe right here in space, this is what you'd call 10 volts. Okay. Well, if we move perpendicular to that line, if we go down, you're still at 10 volts, still at 10 volts, still at 10 volts, still at 10 volts. Since it's a uniform field to the right, we're staying perpendicular to it at all times. We're always at 10 volts. So that's what we'd call, if we're not being careful, we call that the 10 volt line. We might call it, it should be the 10 volt surface. But when we draw in 2D, often, you know, they look like lines. And here might be the 9 volt line, and here might be 8 volt line or surface. Right? So there's your equipotentials. They're just evenly spaced in a uniform field because all you're doing is drawing lines that are perpendicular. And they're actually two-dimensional planes in the plane of the board. These equipotential surfaces can be drawn even on complicated fields because all you really have to do is draw the line perpendicular to the field at every point. So let's look at some crazy field. I'll kind of have one field lines coming in like that. Like that, and they kind of come in like that. And another one comes in like that. And we'll have the field pointing in that direction. Those are the field lines. So let's see, you could come here right down the center and say this is some potential. And that's an equipotential surface, because remember it sticks in the plane of the board. That's perpendicular. It's equipotential because I'm always perpendicular to the field. Then you add another one next to it, might be kind of like this. And another one coming like that, might be kind of like that. And then as you get farther away, they're going to kind of have to start to curve to remain equipotential like that. And you know, you can sort of let your right brain go crazy. Or is it your left brain? I'm not sure. I guess this is both. I'm using my entire brain now. There you go. Oh, let's just stick one more in like that. You'll see why in a minute. So there you go. There's a bunch of equipotential surfaces. You could say, okay, let's make this one 10 volt, 9 volt, 8 volt, 7 volt, 6 volt, 5 volt, 4 volt, 3 volt, 2 volt. And if you move across any of those lines, you're always at the same potential. If you move between the lines, then the potential is changing, and that's because that's the field is in that direction. So one reason you can take, you know, this is a complicated situation. I'm not giving you the equations to describe this. I'm just drawing the field lines in a complicated situation. But we can still use it to do problems. Because what I want you to remember is that the potential, it's not equal to the energy. I'm going to draw an arrow to be vague. I'm not saying potential equals energy. You know that it doesn't. You know it equals potential energy per unit charge. But it's related to the energy. That's why we deal with potential. Some problems are easier done with energy. So let's imagine a charge of mass m and charge, that's kind of redundant, charge q, goes from point A to point B. Let's say it goes from here, and it just flies along somehow and gets to here under its own volition. Right? So this charge, mass m, charge q, goes from A to B and starts at rest. Right? So how fast it be? So what you have to remember is that these are literally potentials. And if you take a potential and you multiply it by charge, you have potential energy. So if this thing is sitting here at rest and it's released and it flies along a field line and it ends up at B, you actually know how much energy it picked up because you know how much potential energy it lost. Right? In this case, it lost because it went, if it's a positive charge, it's definitely going to fly along the field line. Right? So it's going to go this way, and its potential energy is going to go down from 9 down to 4. Okay? So delta U is going to be the potential it ended at, 4 volts minus where it began, but you got to multiply it by Q. So it's going to be minus, or it's going to be Q times 4 volts minus Q times, started at 9 volts. So the energy it lost is basically going to be 5 volts times Q. If you were given the actual charge in coulombs in the problem, you would be able to put it in joules if you wanted to. So the amount that you lose, well, that's equal to the, you're going to lose 5 volts times Q. So you can say 5 volts times Q equals the kinetic that you gain. Okay? So it's going to start from rest. It's going to speed up and fly over here. That's going to be equal to 1/2 mv squared. And that's the velocity at B right there. So if you were given a known mass, you could plug that in and you could solve this for V and get it in meters per second. So a lot of times the reason we draw these equipotential surfaces is to think about how much energy does a charge have as we move around in here. So if you let one fly from A to B, you can think about how much kinetic energy does it gain. If I say I forced one to go from here to here, how much work did I do? Well, you just look at the difference in the potential. Okay? So that's one way these are useful. This potential diagram of a complicated field illustrates another aspect of the interplay between field and potential. And that is first, let's first remind ourselves then, delta V equals, what is, I forgot, okay, the integral of E dot ds. So we know that's true. We've done that to death. Now, to this, I'm going to apply the fundamental theorem of calculus. Fundamental theorem of calculus. When you take calculus, you may learn basically how to do an integral, right? Area under the curve, it's very intuitive. But of course, the mathematicians have a way to turn it into a bunch of laws and axioms and corollaries that don't make any sense, right? You could write 10 pages on the fundamental theorem of calculus. It actually says many things. One thing it says, though, very clearly, is that doing an integral is kind of like doing a derivative backwards, that they're the opposite of each other. One thing the fundamental theorem of calculus says that if this function is the integral of this function, then this function is the derivative of that function. Taking an integral, taking a derivative are like inverse processes of each other. In fact, integrals are sometimes called antiderivatives. Okay? So what that tells us is you can get E from the potential. You can get the field from the potential. And it looks something like this. In one dimension, E, we don't worry about the vector if it's in one dimension, E is minus dV dx, what I just said. If the V is the integral of E, then E is a derivative of V, and the minus sign is just along for the right. So that's in 1D. If you want to do the full 3D vector calculus version in Cartesian coordinates, it would look like this, and this may kind of make sense to you, minus the derivative of V in the x direction, that's the x component, minus the derivative of V in the y direction, that's the j component, and minus the derivative of the field V in the z direction, that's the k component. And you may notice I'm kind of styling on my derivatives now, like they're missing a stem. Did I just kind of lose it, or did I get lazy? Well, that's actually this is a different kind of derivative. When you do derivatives in more than one dimension, you start to use something called partial derivatives sometimes. So we don't care that much about the vector calc. Right now we don't have to really worry about that, but there's a region. These are not d's, these are d's. Okay, it's a special kind of a d we use for partial derivative. But it is basically the same idea, that if it's integral this way, it's derivative the other way. So from here, we can actually see it a little bit. I attempted to draw it that way, is what would be dv dx? That's basically telling me how often to draw the line, okay? So if I'm drawing these lines such that they're evenly spaced in energy, which I did, 10 volts, 9 volts, 8, 7, 6, 5, 4, 3, 2, they're spaced by 1 volt, then the separation I put between them is basically the derivative. It's the change in voltage divided by the change in distance, right? It's 1 volt per a big distance here, that's small. It's 1 volt over a small distance here, that's big. And that's supposed to represent that dv dx, how big the field is. There's a negative sign, but don't worry about that, okay? So here, where the field is small, and you can see from the vector flux the field is small, right? Because over a big, where these 4 field lines are doing a big area, I have a big spacing between my field, my equipotential surfaces. A big spacing means for 1 volt I have a big dx, so it's small. Right? So low vector flux, big equipotential spacing. And then here, where the field gets big, you know, we have a higher vector flux. We have a lot of field going through this area. Then I made the spacing smaller. And then when the field gets weak again, I made the spacing bigger. Okay, so equipotential lines should do that. If we draw them around a sphere, we know that the field gets lower as you go away from the sphere. So really, if you did equipotential lines that are at constant spacing, they would be close when you're close to the sphere, and they would get farther and farther away as you go farther and farther away from the sphere. So that's also something you can use to visualize fields. If we show you a diagram and say the potential is sloping up here, and then it's constant, it's sloping down, you can start to think about what is the field doing. If it's sloping up, the field is pointing back, right, because of the negative sign. So we'll probably do some problems like that in the homework.